I took calculus in high school, and I hated it. I took it because I was told that I needed calculus to get into a good college. And when I got into college, I was told that I needed calculus to get a good job. And when I got a job, I was told that I didn't need to know calculus. Now that I've had some time to think about it, I probably learned calculus for all of the wrong reasons. Learning Julia has given me a reason to re-educate myself on many different subjects that I previously thought that I disliked. So can I use Julia to relearn calculus? Well, let's find out. Welcome to Doga.jl, where I explore the vast Julia wilderness and turn my discoveries into wholesome Julia tutorials. Knowledge of calculus is not required for this tutorial, but I am assuming that you know how to use Julia and that you know how to use Pluto notebooks. In this tutorial, I'll start with a brief history of calculus that will lead us to the subject of automatic differentiation. By the end of this tutorial, you'll understand what automatic differentiation is and what it has to do with calculus. You'll also see examples of how to solve calculus problems using both forward mode automatic differentiation and reverse mode automatic differentiation. With that said, let's get started. Here's a fun fact. Harvard University was founded in 1636, making it the oldest institution of higher education in the United States. Shockingly, the first students at Harvard were not required to learn calculus. That's because calculus had not been invented yet. Yes, that's correct. Harvard is older than calculus. Modern calculus was developed in the late 1600s by Sir Isaac Newton in England and Gottfried Wilhelm Leibniz in Germany. Newton developed calculus first, but kept it mainly to himself and his close associates. Leibniz, however, was the first to publish his work on calculus and actively publicized it. When Newton found out, Newton accused Leibniz of plagiarism. The question of who actually invented calculus is a story for another video. But today, historians generally agree that Newton and Leibniz both came up with calculus independent of each other. Newton and Leibniz approached calculus with different motivations, but they ended up at the same place. Newton's primary interest was in physics, and he realized that the math that he needed to explain the motions of the universe didn't exist yet, which led him to develop calculus for practical reasons. Leibniz, on the other hand, took a more philosophical approach, as he believed that calculus was a metaphysical explanation of change. The term calculus predates both Newton and Leibniz. Calculus is a Latin word meaning small pebble. According to Wikipedia, in ancient times, these small pebbles were used for counting distances, tallying votes, and doing abacus arithmetic. Over time, the word calculus came into use in other languages to refer to any body of mathematics. Today, when we say calculus, we're referring to a specific subject, which is the study of continuous change. There are two main branches of modern calculus, known as differential calculus and integral calculus. I'll be covering differential calculus in this tutorial, and I'll cover integral calculus in the next tutorial. Differential calculus is about instantaneous rates of change and the slopes of curves, while integral calculus is about accumulation of quantities and areas under or between curves. Differential calculus has traditionally been taught in school by teaching students how to solve differential calculus problems by hand. If you want to solve differential calculus problems using a computer, you need to use something called automatic differentiation, also known as AutoDiff, or AD. Ever since computers were invented, folks have been trying to use computers to solve calculus problems. While computers can solve arithmetic and algebra problems similar to the way that humans might solve them, it turns out that computers have a difficult time trying to solve calculus problems the way that humans solve them. Specifically, computers have a difficult time adding really small numbers to relatively large numbers. Since calculus is all about performing calculations using infinitesimal numbers, this is a problem. This problem was first solved by Robert Edwin Wengert. He published a paper in 1964 titled A Simple Automatic Derivative Evaluation Program. The technique he describes in his paper has come to be known as forward-mode automatic differentiation, and thus automatic differentiation was born. In 1980, Bert Spielpenning completed his doctoral dissertation at the University of Illinois at Urbana-Champaign, titled Compiling Fast Partial Derivatives of Functions Given by Algorithms, that describe reverse-mode automatic differentiation, which is the other major technique for a computer to calculate derivatives. Automatic differentiation is a set of computational techniques that transforms the traditional manual process of finding the derivatives of a function into an automated form that can be carried out efficiently and accurately by a computer. So, why is this important? Although automatic differentiation has been around for a few decades, it's recently experiencing a resurgence of interest thanks largely to deep learning. The engine that drives deep learning is automatic differentiation, specifically reverse mode automatic differentiation. In this tutorial, we'll learn how to use Julia to perform both forward mode automatic differentiation as well as reverse mode automatic differentiation. By the end of this tutorial, you'll understand the similarities and differences between forward diff and reverse diff, and you'll have a better understanding of when to use either technique. There are a surprising number of automatic differentiation packages available in the Julia ecosystem. The two packages that I will be covering today are forwarddiff.jl and reversediff.jl. Both packages were created by Jared Revels. It looks like he's moved on to bigger and better projects these days, but he's one of the early Julia developers who's been making significant contributions to the Julia ecosystem ever since the early days. Let's fire up a new Pluto notebook and take a look at forwarddiff.jl, which is the easier of the two packages to use. Let's start by adding the forwarddiff package, as well as plots and Pluto UI. Let's define a generic function to use as an example. For the variable x, let's use a slider. So for any value of x, we can calculate the value of f of x, which I'm assigning to the variable y. Next, let's find the derivative of the function f of x. In English, the word derivative means something that's based on another source. For example, a movie based on a book is a derivative of that book. In calculus, a function based on another function is said to be its derivative. There are several different notations that are used for the derivative, but they all mean the same thing. In calculus, the derivative of a function has a very specific definition. Here, the variable h represents a very small distance from the value x. This equation is basically the formula for the rise over run slope of a line as the distance h approaches 0. The result is a new function, f prime of x, which is the derivative of the function f of x. The process of finding the derivative of a function is called differentiation. Using a computer to find the derivative of a function is called automatic differentiation. We can find the derivative of the function f of x by using the derivative function from the forwarddiff.jl package. The first argument is the function name, and the second argument is the variable name. So given any value of x, we can calculate the value of f of x and the value of f prime of x. Here are a couple ways to think about f prime of x. 1. The value of f prime of x is the instantaneous rate of change. Or 2. The value of f prime of x is the slope of the line that is tangent to the curve at the point x, f of x. For this tutorial, I'm going to give an example of the slope concept. What we're going to do is generate a plot that shows the relationship between x, f of x, and f prime of x. To do that, we need to define a line segment for the line that is tangent to f of x for any value of x. We know from algebra that the equation of a straight line is y equals mx plus b, where m is the slope and b is the y-intercept. In this example, we know the values for x, y, and m, so we can calculate the value of b. X is the value controlled by our slider. Y is the same as f of x. And m is the slope, which is the same as f prime of x. Now that we can calculate the y-intercept for any line that is tangent to f of x, we can also calculate the coordinates of any line segment along that line. The line segment that I'm using will step 1 unit to the left of x and 1 unit to the right of x. Now, all we need to do is generate a plot. Let's add some markdown text so we can see the values for x, f of x, and f prime of x. We need to place the plotting recipes inside of a begin end block, so the code inside of this cell will be a little long. Okay, let's move down our slider and then hide some of these cells. So what are we looking at here? The blue curve is the function f of x. The green dot is the point x comma f of x. As you can see, it's starting at the origin, or the point 0, 0. That orange line segment is a segment of the line that is tangent to f of x at the point x comma f of x. As you can see, the initial slope is -1, so the line is sloping down at a 45-degree angle. The value of the slope of that line is the same as the value of f prime of x, which is the derivative function of f of x. As we move the slider, you can see that the slope of the line segment changes so that the line is always tangent to the curve for any value of x. So what should we be looking for in this plot? First of all, you're looking to see the value of f prime of x is positive, negative, or 0. A positive value means that f of x is increasing in value as you move to the right. A negative value means that f of x is decreasing in value as you move to the right. A value of 0 means that there is a local maximum or local minimum at that point. This is important when solving optimization problems that require finding either the maximum or minimum value of a function. The other thing to pay attention to is the relative magnitude of the value of f prime of x when the value is either positive or negative. Since f prime of x represents the instantaneous rate of change, the relative magnitude of the value of f prime of x will tell you how quickly or how slowly the value of f of x is changing for any value of x. So who would have thought calculus can actually be fun? In this example, we only had one input and one output. It turns out that forwarddiff.jl is very useful for classic calculus problems, not unlike problems you might encounter in an Intro to Calculus course. But in modern applications, you might need to find the derivative of a function that takes multiple inputs and returns multiple outputs. For more complex problems, you need to use reverse mode automatic differentiation. In reverse mode, there are two passes in the automatic differentiation process. The first pass is a forward pass, and then the second pass is the reverse pass. Without getting into the details of how this works, it's this reverse pass which allows reverse mode automatic differentiation the ability to tackle more complex problems. To see this in action, let's create another Pluto notebook. I took the code for this section from the examples folder in the GitHub repository of the reversediff.jl package. For this notebook, all we need is the reversediff.jl package. This function is from the reversediff.jl example file. In this example, the variables a and b are matrices filled with random numbers. The first 100 by 100 matrix is matrix A, and the second 100 by 100 matrix is matrix B. even though there are a lot of inputs, the output of the function f of a comma b is a single number. The reversediff.jl package requires the inputs to be a tuple of abstract arrays. Now, we can use the reversediff.jl package to find the gradient. Conceptually, a gradient is the same as a derivative, but the term gradient is typically used for functions with several inputs and a single output. To find the gradient, simply use the gradient function from the reversediff.jl package. The first argument is the function name, and the second argument is the name of the inputs. The inputs need to be some type of abstract array. What you're looking at is two partial derivatives. A partial derivative is defined as the derivative of a function of two or more variables with respect to one variable. The first matrix is the derivative of the function with respect to a. The second matrix is the derivative of the function with respect to b. Each element in the matrices is the value of the derivative function for their corresponding input value. Everything that you see here is called the gradient of the function. As you can see, this gradient is much more difficult to interpret and much more difficult to visualize. The good news is that if you're using a deep learning package like Flux.jl, all of these calculations are happening under the hood, so you don't need to worry about it. The purpose of showing you this example is simply to demonstrate that the reversediff.jl package can handle complex problems very efficiently. On that note, I need to point out that the code that I used is not the optimal code. The example file in the reversediff.jl GitHub repo contains an optimal version of this example, which requires several more steps. I'm not going to go through these extra steps in this tutorial because I think that it's more important to grasp the basic concepts first before trying to optimize the code. But if you're interested, I provided a link to the example file in the description below. So there wasn't a lot of code today, but there were quite a few concepts. So let's break here, and I'll share some final thoughts. When deciding whether to use fordiff.jl or reversediff.jl, here are some general rules of thumb to consider. Fordiff.jl is easier to use, and it's ideal when the number of inputs is less than the number of outputs. An example use case for fordiff.jl would be a typical problem from a calculus class. Reversediff.jl is more difficult to use, and it's ideal when the number of inputs is greater than the number of outputs. An example use case for reversediff.jl would be deep learning. If you found these packages to be useful and interesting, you can show your appreciation to the creator and contributors by going to their respective GitHub pages and leaving them a star. Maybe reversediff was a little too complicated for a beginner, but forwarddiff is definitely a great starting point if you're like me and looking to discover or rediscover the joys of calculus by using Julia. If you made it this far, congratulations! If you enjoyed this video and you feel like you learned something new, then please consider smashing that like button, leaving a comment, sharing this video, and subscribing to this channel. If you'd like to support the educational work that I'm doing, then please consider using the Super Thanks button. For ongoing support, please consider joining and becoming a channel member. Channel members get ad-free, early access to all of my new videos. Thanks for watching, and good luck on your Julia journey.